Let's learn about the incredible vector. What is a vector? Well, it is a quantity or a directed distance with both direction and magnitude. And the symbol looks like that. Okay. Well, what do I mean by that? Let's take the first piece right here, direction. Well, the direction, that's just telling me it has, well, which way is it pointing? Is it going that way? No, this one actually is going this way. Okay. So in order to give it direction, we need to give it an angle. I'm starting here, and, well, if I tell you 30 degrees, well, now you know that it's going 30 degrees. If I gave you 195, for example, well, that would be somewhere over here in the third quadrant going that way. Okay? So the angle tells you the direction, and the magnitude, well, the magnitude represents the length of the vector. Okay? Magnitude is the force. I don't want to get ahead of ourselves, but why do we learn vectors? Vectors represent force on an object. And the bigger the vector, the more force. The smaller the object, the smaller force. Okay? And then we use that to in applications. Right here is the definition of the magnitude. It is the length of the vector. Okay? So when you find the length of it, you know how much force you have. The symbol for it is right here. It's the absolute value sign. It's just because it's length, and we can't have negative. So distance can't be negative. So that's the symbol we use. And in order to give this thing direction, I do have to tell you where we're starting, right? We usually start, in standard position. Standard position is what you think of normally. It's starting right here at the positive x-axis, and then, 0 degrees, and then you move up from here. Notice how I say the positive x-axis. This is the positive x side, and the negative side would be over there. And the same thing with the y's. You'd have your positive y's up here and your negative y's down there. So that's why I specify positive. We're not starting over here. Okay, so that's that. Amplitude. Well, the amplitude is the direction there. It is the theta, okay, the directed angle between the positive x-axis and the vector we have. So the amplitude tells us the direction. Over here, I have a nice picture. Let me move that into the front. You're going to hear us talk about the tail and the head. Well, we start somewhere and we end somewhere. The direction, I have a tail here, I start here, and it goes in the direction up to the head. Okay? And the head is always the arrow, and that's which way it's going. And while I make this a little smaller, if you need to copy any of this in your notes, please just hit your pause button and do so. All right, never lose sight of what that definition of a vector is. The definition of a vector is it has direction and, oh, there's my little picture. It has direction and magnitude, okay? I have a specific angle where it's pointing. That would be the direction of it, and the magnitude is the length of it. So long as those two properties hold, it's the same exact vector, okay? If I had another vector that looked just like v, I could call them equivalent vectors. And also, whether vector v is over here, or it doesn't matter where I translate it, if it still has the same direction and the same magnitude, it's an equivalent vector. That comes into play when we're doing geometric vectors. Because say I had vector u over here and vector v over here, and I want to add the two of them. Well, I can't add them the way they are, but because we are allowed to translate these, and just as long as we're keeping the same direction and magnitude, I can move it over here. And that is how you add two vectors. You start at the tail and you go to the head, and then you pick up here again and you go tail to head. Tail, head. All right, well, that would be u plus v, but the vector u plus v is the shortcut. The shortcut between these two would look something like this. How does that look? Good enough. That purple one right there is u plus v. Vector u plus vector v. Okay, that is that. It's the shortcut between the two vectors. Where did we start? We started over here. Where are we ending? We ended up there. It's also known as the resultant. The resultant, you also might remember that as the diagonal of a parallelogram. That's true, but that's if you're only adding two vectors. You could be adding more than two vectors. Okay, but the resultant is the sum of two or more vectors. All right, what else we got here? Well, why don't we add vector w now? Okay, say we're going to do vector v plus vector w. All right, so right here is vector v, and right here is vector w. If I'm going to add the two of them, let's do the same thing and put it tail to head, tail to head. All right, so now we have this. Vector v plus vector w. Well, this is where we started, and that's where we're ending, so right there is where the shortcut would be. Let's use this gray one and see if we can't get that nice and close enough. Close enough. Okay, close enough for government work. Okay, that gray one right there represents, hold on a second, let me do that and move that up there. And is that gray enough? Let's see. That's gray enough. Oh, that looks pretty close. That gray vector represents vector v plus vector w. Okay, the shortcut. Cool. All right, well, now let's add another vector. Let's take vector x here. Okay. Now, before I add it, I want to just talk about parallel and opposite vectors for a minute. Okay, so vector x. If I were to tell you that vector x and vector v have the same length, they're just in completely opposite directions. So say this has the same length as that. But notice how vector v is pointing that way and vector x is pointing that way. If I were to translate it over here, come on, vector x, it's just pointing in 180 degrees in the opposite direction. Those are opposite vectors. So if you look at this picture up here, okay, opposite vectors, let me bring that to front. Okay, opposite vectors have the same magnitude, just opposite directions, and that's exactly what we have here with vector x and vector v. I can denote them by just negating it. If this is vector v like we have here, well then vector negative v would just be you turn it around 180 degrees. Therefore, I can call this vector over here either vector x or vector negative v. It is the exact same vector. Let's translate vector x or vector negative v, which are the same, over here. Oh, and I moved that. I'm sorry. Let's move it back. Cool. So now what do we got here? So it's the purple one right here. So I just went vector w plus vector x, which would be sort of this one, but it's the opposite of that. It would be pointing in the other direction. Don't forget, you need to be, here, let me get some color here. How about make that bigger, and we'll use yellow. The only difference is it is now going that's not yellow, that's red. Anyway, it's now going in that direction because don't forget, we started here, we went this way, and then we went that way, and we ended here. There's our end point right there, okay? So, this red one that we just drew, we could represent that a couple different ways. That is the same thing as taking vector w plus vector x, which is also the exact same thing as if I were to do vector w plus vector negative v, because x and negative v are the same vector. This bottom one right here is, if you were given on homework assignment, would look like this. It would be subtraction. Okay. If you were subtracting a vector, I want you to always think of adding them the same way. You're adding it, you're just adding a negative vector. If you are coming across a subtraction problem like so, just treat it as vector w plus vector negative v. You're adding to it the opposite of v. Okay. And my last little call out here, parallel vectors. Yeah, I forgot about it, but it's what you would think. Okay, parallel vectors, they can be the same, they're going in the same or opposite direction because they'd be parallel, they just have the same slope. Okay, whether the arrow is pointing up or down, they would have the same slope. Let's try this one out for size. Now, this example doesn't deal directly with vectors, but it's an application that we're going to be using in a couple days. So work with me. Find the amplitude to the nearest tenth of a degree. If you remember, the amplitude is right here. Let me get a color. It is this angle that we're directing our view up. That would be the direction, the angle. That's your amplitude. We got to find that angle. In algebra, you might remember that as the angle of elevation. Okay, that's what this is in this example. Okay. All right, well, say you are standing right here, and you have a friend who's standing on top of the building over here, and your friend looks down at you and says, "Hey, buddy, what up?" And you want to look up and you want to see your friend, but you need to know exactly what angle you should raise your head up to see this person. That would be your amplitude. Well, say you are standing 520 feet away from the building, and the building itself is 475 feet. That's a 4. And yes, you are safe. It's safe to assume that that's a 90-degree angle. So when you have a right triangle and you're dealing with angles and side lengths, it's a safe bet that we are going to be using SOHCAHTOA. You have to have this memorized if you don't already, okay? Some old hippie caught another hippie tripping over apples. That is a nice, easy way to memorize that. Well, what is the opposite, adjacent, and the hypotenuse? Well, if this is the angle, if I go across from the angle, that gives us the opposite side from the angle. Here's my hypotenuse. The hypotenuse is always across from your 90-degree angle, which makes this 520 our adjacent side. Well, what do we got? We know the adjacent value, and we know the opposite value. We don't know anything about the hypotenuse, so this side would help us, and this side would help us. Well, which one uses opposite and adjacent? Opposite and adjacent is tangent. You could use Pythagorean theorem, find the hypotenuse to use one of these other two, but why? It's just extra work. Let's do the tangent of our angle. Tangent of the angle. If you know the angle, you plug it in. If you don't, it's unknown. Now I'm going to call it theta. Tangent of theta equals your opposite side, which is 475, over the adjacent side, which is 520. All right, so at this point, what do? Well, we want to find theta, not tan of theta. So if we multiply it by the arctan, and we got to do the same thing to both sides, I'm going to take the arctan of both sides. Tan and arctan cancel each other out, and we have theta. And that's going to leave us with arctan of 475 over 520. That is the second tan function in your calculator. You're going to plug that in, and you're going to look at your calculator, and you're going to round it to the right place. Here it says the tenth. So we should get a value of 42.4 degrees. So if I want to see my buddy up on top of that building, I have to look up 42.4 degrees from ground level. Pretty cool. All right, so hopefully that was somewhat enlightening. Let's see what we're working on in class tomorrow. Okay, this outline is slightly different than what you have, but either way, this is what we're doing tomorrow. We just talked about geometric vectors. Day 1. We have a handout. We will work on those in class. See you then.